Hello, welcome to part 2 of the quantum electrodynamics series. The previous episode explained how light is in fact particles and not waves. It also covered how these particles are governed by probability and not certainty. We've also covered probability amplitudes. Those are the little arrows. Those probability amplitudes have a length which is the square root of the probability of the event, and the stopwatch analogy helps us understand why it rotates. We're going to cover a few new examples, a few new rules in this episode. Here's the setup. S is the source. It emits red photons. P is the photomultiplier. It detects photons. We have a mirror, and we also have a screen to stop photons travelling directly from the source to the photomultiplier. Let's get on with it. Expectation. All the light that gets to P reflects on the point where angle of incidence equals angle of reflection. This is what we know from school. Obviously the parts of the mirror near the ends will not reflect photons onto P. We're gonna do the ends of the mirror anyway, because remember, this is physics. We can't really expect what we want to happen to always happen. We will use the same method as we used last episode. Make arrows for each and every way the event can happen, and then combine them. There are actually a vast number of ways this can happen. So instead we're going to generalize. We're going to split the mirror into sections. We're going to label A through to P. We say the photon could bounce off the mirror at A, it could bounce off the mirror where you think it will, G, or it could also bounce up off the mirror, back onto the reflector from P. You're probably thinking this makes absolutely no sense because the angle of incidence does not equal the angle of reflection for anywhere but where the photon is bouncing at G. But please bear with me. We're obviously ignoring the fact that this would happen in 3 dimensions, but it doesn't really make any difference, and it would really mess up my diagrams if I had to draw them in 3 dimensions. So please, we'll do it in 2 dimensions. Let's move on to the arrows. So obviously the arrow for G is the longest arrow. No, we can't just assume that. Sorry. In fact, all the arrows have essentially the same length. The length may be the same for each arrow, but the direction the arrow is facing is going to be different for each arrow. This path is obviously longer than this path. This path essentially goes away from the detector until it hits the mirror, so it must take far longer. Time for the graph. The time taken to get there is on the y-axis. The strip letter is on the x-axis. Time taken to get to the detector from A is high because it's a very indirect path. As we move towards G, the paths get more and more direct, so the time taken becomes less. As we move past G, the time taken increases because the paths become less and less direct. I mean, look at M. It essentially overshoots the mirror and then bounces back up. Since the source and the detector are actually the same height, we get this nice symmetrical curve. That wasn't an accident. We set it up like that because we wanted a nice smooth curve. We get these arrows for the strips. The direction corresponds to the directions the stopwatch is facing when it gets to the detector. As B and A take largely different times, this is because the difference in length of the path is quite large, the arrows point in very different directions. We then get this spiral shape emerging until we move to the centre. As we get to F and G, the stopwatch is facing largely in the same direction, because these paths are very similar in length. So we get a straightish bit. Then we get another spiral as we move past G. When we get this final arrow, the length isn't actually that bad. QED predicts that light will reflect off the mirror! Woohoo! When we look a little deeper, we see that the ends of the mirror pretty much don't do anything, and that the only part that actually makes any difference is the middle of the mirror. In the end, we see the behaviour that light actually reflects off the centre of the mirror. When the time for the path was least, the differences in time between neighbouring paths were also least. We're going to make a crude claim here. Light travels in the path of least time. As we saw, light reflected off the centre of the mirror because time was least there. Since pretty much all the reflection is happening at the centre of the mirror, we really need to prove that reflection is actually happening over the whole of the mirror, but it's just cancelling out. Let's bin most of the mirror and only keep this bit on the left. The mirror may be big, but it has pretty much no chance of actually reflecting into the detector. Now there is something we can do other than move the mirror that will make it reflect into the detector. In the last experiment, the arrows on the left-hand side of the mirror were pointing in different directions, which caused the final reflection of this to be essentially nothing. If we zoom in, and make the strips really small, we can see the difference in time for neighbouring paths is really small. We see that some arrows point more or less to the right, and some more or less to the left. When we add up all the arrows, we get a circle. This shows that we don't get any reflection, as we expected. Now if we took a knife and we scraped off the parts of the mirror with a bias in a particular direction, say to the left, then we'd end up with a mirror that reflected, because the final arrows would make semicircles. We add these arrows up and we get a big final arrow. Quantum electrodynamics predicts this will reflect really well. It does. It's called a diffraction grating. We've essentially started with a mirror that didn't reflect. We scraped off half the mirror, and we ended up with a mirror that did reflect. This particular diffraction grating is actually tailor-fit for red light though. It would not work for blue light. However, if we moved down the detector just a little bit, we would actually detect blue photons. If you shine white light down on the diffraction grating, you actually get the colours to separate. This is what a DVD does. That's why it's so cool. We've learned here that we can't just ignore the parts of the mirror we don't think are going to reflect. We actually have to look at the whole mirror and every way that the event can happen. Otherwise, we're doing it wrong. Let's move on to light going from air to water. Here's the setup. S is the source, P is the photomultiplier. White is air, blue is water. We separate into strips, make a graph. It looks very similar to the graph we made earlier. Almost like I copied it, so I wouldn't have to make two of them. Remember, light travels slower in water than it does in air. Suppose you and your two friends are challenged to get from here on the beach to here in the water. Obviously you swim slower than you run. You all move at the same pace. Brian sees the point and decided to go straight for it. Charlie runs as close as he can to the point, then swims for it. As quick-thinking individuals, we realise that Andy should run neither of these routes, as they are not the fastest route. The fastest route is running to the point of perfect balance between smallest possible distance and smallest possible amount of water to swim. Hence, Andy would win. Light also picks the path of least time. Light follows the path through G for exactly the same reason that it reflects when I equals R. When we combine all these arrows, we see that the majority of the contribution is coming from the path of least time and its surrounding path. When we combine all these arrows, we get the same shape as we did before.